Hello dear students, welcome you all to the next lecture of the JCE eConnect series of online lectures. We are studying module 5, which is anchorage zone stresses in post-tensioned members. In the previous lectures, we have understood how the forces act in the anchor zone and what impact they cause. Further, we discussed the IS code regulations for obtaining the bursting stresses, and then we started with solving some examples. So in today's lecture, we'll go ahead with the example. We'll try to solve a new type of example wherein the application of a duct, okay, when a duct is there, what impact it has on the section as well as the stresses, we'll try to understand in this video. So today we are starting with example number 3. So let's go through the example. An end block of a post tension beam has a cross section of 80 mm by 160 mm, is pre-stressed using 7 mm diameter wire carrying an effective pre-stress of 1200 Newton per mm square using concentric anchor plate of 50 mm by 50 mm. A duct of 20 mm diameter is provided. The cube strength of concrete at transfer is 35 Newton per mm square. Check the beam for bearing pressure. The grade of reinforcement to be used is Fe250. Also determine the thickness of the anchor plate. The maximum permissible shear in steel is 94.5 Newton per mm square. So now when we look at the problem, maximum data is similar to the one which was there in the previous examples, but some things are there in addition which we have to note. Firstly, we have a duct of 20 mm diameter. Okay, duct means a opening of 20 mm diameter is provided in the beam. Secondly, along with the check for bearing pressure, okay, here what we have to do is we have to determine the thickness of the anchor plate also, and the maximum permissible shear is given as 94.5. That means that these given values will be used somewhere. And the other thing to be noted in the example is nothing about the bursting force is asked nor the reinforcement is asked. The problem is straightforward. Okay, it is from one of the question papers. It is a bit confusing problem because in this module you will be in the mode of solving examples on bursting force, but here they have just asked for the check for bearing, and further what is required is the thickness of the anchor plate to be provided. The size is mentioned, one size is mentioned as 50 by 50, but the thickness is not known. Okay, so let's start with the example. So firstly, I have put up a sketch. Width of the beam mentioned is 80 mm. Okay, the depth of the beam is 160 mm, which is divided into two parts of 80 by 80, and the width is divided into two sections of 40 by 40. You have a plate which is there in highlighted in pink color of size 50 by 50, and the extra addition is this duct of 20 mm diameter. So how this duct will impact the calculation we'll see while solving the examples. So hopefully the figure is clear. Now with this you should be able to note down the values of y naught, yp naught. Okay. So from the figure we can take the value of y naught as 40, yp naught as 25. Given value of the strength of concrete is 35 Newton per mm square. The effective stress is 1200 Newton per mm square. Maximum permissible shear in steel is 94.5. Now, why we should take the value of y naught as 40? It is because we have to compare two sides. One is the width, okay, second is the depth. The one side will be equal to 2 times of y naught. Either we have to take 80 mm side or 160 mm side. Now which side we have to choose is which is the smallest. So in this case, as we have a section of 80 by 160, the smallest size will be 80 mm, which is the width of the beam. So this 80 mm is nothing but 2 times of y0. Hence y0 will be 80 by 2, which is 40. Okay, so whenever you get a rectangle, see that the y0 value is the half of the smallest side, either the width or the depth. Then secondly, we have a plate of 50. One side of the plate represents 2 yp0, and hence yp0 will be the side that is 50 divided by 2, which is 25. So these both values you have to be careful, because these are the values of high importance and they will be used in all the important calculation in this problems. Okay, so hopefully this thing is clear. Then what we need to find? We need to check for bearing pressure. Then we need to find the thickness of the anchor plate. Check for bearing pressure. Now this step is similar or exactly the same as we have done in the previous problems. Firstly, we will find the punching area. A punching is 2 times of yp0 into 2 times of yp0. It is nothing but the area of the plate. Okay, it is the area of the plate, which is 50 by 50. We get the answer of 2500 mm square. Next, area of bearing. Now here we have to note the very important change. Generally we used to find area of bearing as 2y0 into 2y0, which was the smallest side of the section. But here, as a duct is provided, that means a hole is made, a hole is drilled in the section, which is of size 20 mm diameter. Hence area of that duct has to be deducted when we calculate the area of bearing. It does not affect the punching, because in calculation of punching the duct will not be affected, entire plate will be subjected to punching. But when we say bearing, okay, that is force upon area is bearing, here this area is not available at all for taking the bearing, as it is already cut out. Okay, so this area has to be deducted when we are calculating area of bearing. Remember, whenever a duct is given, okay, whenever a duct is given, this area needs to be deducted compulsorily when we are finding the area for bearing. So 2y0 multiplied by 2y0 minus area of the duct. Okay, what is 20? 20 mm is the diameter of the duct given. So this is how the calculation goes. Therefore, substituting the values, we get an area of 6085.840 mm square. So we got the area of bearing as well as we got the area of punching. Hopefully this is clear. Next, as we have been given the effective stress, we need to find out the effective pre-stressing force, that is P effective. Okay, so P effective will be 1200, which is nothing but the pre-stress. Okay, 1200 is the pre-stress into pi by 4 into 7 square. Here 7 is the diameter of the wire which is used for pre-stressing. Okay, 7 is single wire of 7 mm dia is used. So 7 square is the diameter of the wire used. Therefore, we get an effective pre-stressing force of 46.18 kilonewton. Now during valuation we find that students in a hurry just take 1200 itself as the effective force. Okay, 1200 itself as the effective force, whereas it is not the effective force. Okay, it is the effective pre-stress. It has to be multiplied by the area of the wire to get the effective force. Now I have missed out here, I think, into 10 raised to 3 as the unit is kilonewton. Please all of you make a note that here it is 1200 kilonewton. Okay, so 1200 kilonewton, hence the answer is also in kilonewton. So here we find the P effective force. Next, actual bearing pressure. We get the actual bearing pressure as P effective upon area of bearing. So, substituting the required values, we get an bearing pressure of 7.6 Newton per mm square. Okay, so total effect of the bearing on the section is 7.6 Newton per mm square, which is not that great force, okay, or not that great pressure, and generally it will be satisfied with the available section. As per IS 1343, the bearing stress permitted is the least of first clauses 0.48 FCI square root of area of bearing upon area of punching, which is equal to 0.48 into 35 into square root of 6085.80 divided by area of punching is 2500. So we get the first option as 26.21. Second is 0.8 times of FCI, which is 0.8 into 35, we get an answer of 28. Whereas our actual bearing pressure was something 7.1. So both the values, if we take, the least one is 26.12, which is comfortably greater than the actual bearing pressure. Hence we can say that the section is safe. So up to here, the problem which we solved was quite similar and or same to the previous examples. Now the new application which is introduced in this example is but still as a part of the routine, I am just calculating the bursting force. Okay, again I am repeating, we are not designing the reinforcement here. So even if you don't find the bursting force, okay, it will not have any effect. But if a statement is added in the example that bursting force is also required, okay, so considering that, I am keeping this bursting force calculation also in the example. So calculation of bursting force is quite easy. As per IS 1343, we have the formula for bursting force. FBST is equal to Pk into bracket 0.32 minus 0.3 into Yp naught upon Y naught, where Pk is the effective pre-stressing force, which we have found out as 46.18 into 10 raised to 3. Substituting the value of Yp naught is 40, Y naught is 80, we get the bursting force as 7850.6 Newton. Now secondly, when you look at the example, see the section given is very small. Okay, it is hardly 80 by 160. So that's why in this example the design of reinforcement is not asked. But you may get an example wherein you will have to design the reinforcement also. Along with that, you have to calculate the thickness of the plate, which we will be doing in the next step. So this is just the repetitive calculation for bursting force. This is exactly not required in the example, but still if you add this step also, there won't be any issue as such. So next is to determine the thickness of the anchor plate. Now this is the change, this thing we are solving for the first time. It is obtained by equating resisting force is equal to punching force. The resisting force is equal to P effective, which is 46.18 into 10 raised to 3. This is nothing but your pre-stress, which is effective pre-stress which is applied. Punching force is given by the circumference into the plate thickness multiplied by permissible shear stress. Okay, so this is a new formula. Okay, circumference into plate thickness into shear stress. Now circumference is the circumference of the duct. Okay, the duct is of 20 mm diameter. Pi into 20, because the formula for circumference is pi d. So here pi multiplied by 20 into thickness of the plate, T is unknown, into permissible shear stress is given as 94.5. So this 94.5 is a given data. So now we have two equation. Equation 1 is for the resisting force, equation 2 is for the punching force. So in the next step, when we equate equation 1 and 2, the only unknown in this equation will be T, and solving we get the value of T as 7.78 mm. Therefore, we can provide a plate of 8 mm thickness. So this is a simple straightforward calculation. This will be asked for 3 to 4 marks. Okay, so resisting force and punching force, the calculation should be quite easy because it is a straightforward calculation with the proper substitution. Only the care which you have to take is while finding the circumference, you have to substitute the diameter of the duct and not the diameter of the wires. Okay, the diameter of the duct has to be used while calculating this value of circumference. Then plate thickness is unknown and the shear stress is given. So by simple substitution and equating equation 1 with 2, we can obtain the thickness of the plate. Further, you can round off to the next value. So generally 8 mm, 10 mm thick, 12 mm thick plates are available. So this is the example number 3. In the next lecture, I'll come up with an example which has a circular plate in an I section. Hopefully you are keeping up with your studies, and be serious now. If you have not made the notes and all, please start making the notes. We might include this topic also for your first internals, which will be there in first week of June. Thank you all.